Okay, one little new thing, and I'm going to put it all together and finally talk about these standing wave things. When we started talking about waves, so the first note that I called wave basics, set up in there, basically what we said is if an object is elastic, that means it has a tendency to snap back to its original shape. Objects that are elastic will vibrate. Now, what I tried to get you to notice is that when things vibrate, they always vibrate at a particular frequency that depends on its physical size and shape. So if you didn't do it, go get your ruler back out and play with your ruler. If you've got the ruler hung in a particular orientation, it's always going to sound the same way. Unless you change the ruler, how much is hanging over the edge, where you're holding it, it'll always vibrate at a particular frequency. That particular frequency that depends on its size and shape and the physical properties of it, that's called its natural frequency. Sometimes it's called the resonant frequency. If you played with wine glasses, like an empty wine glass, when you ting it, it's always going to vibrate at the same frequency. That's the wine glass's natural frequency. If you put a bit of water into the wine glass, it will vibrate at a different frequency, but unless you change the water, always the same frequency. That's the natural frequency or resonant frequency of the wine glass when it has that much water in it. Based on their physical properties, their size and shape, all objects tend to vibrate at this particular frequency. So we can say that every object that's elastic can vibrate, and every elastic object has this resonant or natural frequency that they vibrate at when they're disturbed. Play with the ruler or ting the wine glass. Now here's what resonance is. Let's say you've got something like your wine glass or your ruler just sitting there in its particular physical setup, and something else in the room starts to vibrate, maybe a speaker, and the vibration of that something else matches the resonant frequency of your elastic object. Then that elastic object, the wine glass or the ruler, receives that energy really efficiently. And as it receives the energy, the elastic object, even though you didn't touch it, will start to vibrate with bigger and bigger amplitudes. So this is the classic wine glass, and if the singer sings at the right note, then the energy of the singing gets given to the wine glass and the wine glass will start to vibrate. If they do it right, the increasing amplitude part means that we could get to the point where the wine glass shatters. A common everyday world example is, imagine you take a kid to a swing, or imagine when you were a kid on a swing. You can go higher by pumping your legs, and if you think about it, you pump your legs in a particular rhythm or frequency to make yourself go really high. That's increasing amplitude. Or the kid on a swing could ask for a push. If you're the pusher, so let's pretend you're pushing the kid on the swing, you're not going to push just at any old time. You're going to push every time the kid gets back to you. Basically, you're adding energy, or you're pushing at the resonant frequency of the swing. And by pushing at intervals, by delivering energy at the same frequency as the natural frequency of the kid on the swing, then the kid on the swing is going to swing with increasing amplitudes. Next time you're at a park with swings, maybe while someone's swinging, make sure it's someone you know. Don't be weird and start pushing some random stranger, but push them like a little bit early. And you'll notice they don't receive the energy as well. It kind of hurts your hands if you're not careful. But if you push at the right time, then you can get them going with a nice big amplitude. Another example some of you may have heard if you're in band class, music class, sometimes the snare drum will just start to rattle when other instruments play. The snare drum's a neat thing. The springs that are underneath the skin of the drum have a whole bunch of resonant frequencies. So the snare drum rattles when another instrument is playing because that other instrument is matching one of its natural frequencies, so the spring in the snare drum starts to rattle. I had some junky cars in my life, and I had cars where at a particular speed, like the change in the cup holder would start to rattle. I had one junky car where the seatbelt buckle would rattle, and it would only do it at a particular speed. Like when I was driving at 50 kilometers per hour, my seatbelt would rattle. That was also a resonance thing. Something about the motor was going at a particular frequency that matched the resonant frequency of the seatbelt, and when I went that speed, the seatbelt absorbed that energy efficiently and literally it rattled. Very annoying, but a cool physics thing. Okay, now we're going to put it all together. The topic of the day is standing waves, but we needed those sort of background pieces, reflection, phase, interference, resonance to make sense of it all. All of those things come into play in standing waves. What I'd like you to try and do, I'm not very good at it, so I don't have a video of it, but I want you to go back to that simulation, set it to oscillate this time, and play with it, so see if you can get kind of dead spots on the string and kind of lively spots. If you do it right, there'll be like, maybe it's right about here. That spot on the string will always stay on the dotted line. That spot on the string will always stay on the dotted line. And then this part will go up and down. And this part will go up and down. This part will go up and down. But those spots in the middle just stay perfectly still. That's what a standing wave is. Basically, it's all typed up here. But we've got the reflected wave interfering with the wave that the motor created. So we've got waves going this way created by the motor, and we've got reflected waves going back that way. These outgoing waves interfere with the reflected waves. If we set things up right so that the frequency of the motor is just right, then those wavelengths are the right length, that we get some resonance and we get some really big amplitudes. So these lively spots here are going to vibrate really big. That's the increasing amplitude because of resonance. If you could set it up perfectly, you'd have these dead spots that are moving back and forth left to right, and then really, really lively spots. I struggled to get it going well, so I don't have a video of me doing it, but you play around with it, see what you can do. Vocabulary wise, when we can get it, we'll draw them, and we can just make them perfect when we draw them. But when we do it, the dead spots, the physics word for those is we're going to call those nodes. And the part of the slinky with all the motion, the really lively part, those are called antinodes. So nodes are the dead spots, antinodes are the lively spots. If we were really good at playing with that simulation, the slowest frequency, which corresponds to the longest wavelength, that would make one of these weird standing waves, is when we get basically one big crest overlapping with the reflected trough. If we think about it, I'm going to doodle up here a full wavelength. So wavelength, remember, is the length of one wave. A full wavelength would look like that. So basically our longest standing wave that we can fit into a string is when we've chopped the wave kind of here. We've got half of a wavelength fitting into the length of the string. In physics, you'll see these in music too, but this particular standing wave is called the first harmonic or the fundamental. And it's really just a big skipping rope shape, one big antinode. Really what it is it's half a wavelength fitting into the length of a string. So say we set that up, nice big standing wave, basically it's like a big skipping rope. If we changed the frequency and made the wavelength a little bit smaller, we wouldn't get a standing wave. You get a bunch of gobbledygook. We wouldn't have a dead spot that stayed perfectly still. We'd have a dead spot that kind of wandered left and right. That wouldn't be a standing wave. But if we kept playing around, we would get it to the point where the dead spot stayed exactly still. And we had lively spots over here that were wobbling up and down a lot. Lively spots over here that were wobbling up and down a lot. So two nodes, one big ant and one antinode in the middle. Basically what we've got is, I'm struggling today. One full wave fitting into the length of the string, and the wave traveling one way interferes with the wave that reflected back. Basically in the length of the string, however long the string is, we fit one full wavelength. It's got two antinodes and one node. We don't count the end of the string, they were already fixed, so they don't count as nodes. There's one node in the middle. This one has funny names as well. It's called the second harmonic or the first overtone. If we took the motor and we drove it a little bit faster to make a little bit shorter of a wavelength, we're going to get gobbledygook, a mess. But if we keep making it shorter, then it's going to settle, and at some point we're going to get a nice standing wave with two dead spots, so two nodes, three lively areas, and basically what we've got is that's a half a wavelength, that's a half a wavelength, that's a half a wavelength. So we've got three halves or 3 over 2, or 1.5 wavelengths fitting into the length of the string, that makes another standing wave. This particular standing wave has got 3 antinodes and 2 nodes. In between the last situation and this situation, it wouldn't have been a standing wave. There would have been 2 nodes, but they would have been moving all over the place. But if we can get it to the perfect setup that there's 1.5 waves in the length of the string, then it's going to settle down nicely into a standing wave. We call this one the third harmonic, or the second overtone. If we speed it up even faster, we make it a little bit shorter wavelength. It goes gobbly-goopy, messy for a little bit, but then it's going to settle down again. And when it settles down again, it's going to have 4 antinodes and 3 nodes. It's got the name of the fourth harmonic, or the third overtone. You can trace it out. There's 4 of those. I'm gonna call this a football shape. So if I ever talk about a football shape, this is my football shape right there. So this standing wave has 1, 2, 3, 4 football shapes. Each football shape is half a wavelength, so 4 halves means there's 2 full wavelengths in that standing wave. That may sound a little bit weird and coming at you fast and out of left field, but it's not as crazy as it sounds. You don't have to memorize this chart, but there is a little trick to help us get through it. What I'd like you to notice is that there is a connection. There's a connection between the names and the number of nodes and antinodes. There's also a connection between the number of those football shapes and the length of the string. So we'll go back to that chart, see if you can find a pattern in the number of antinodes and nodes and the 2 names, and then see if we can find a connection between the length and the number of footballs. Pause the video if you need to. I'm going to give away the answer. Here's what hopefully you saw. The number of nodes tells you the overtone name. So if I say it's got 2 nodes, that means it's the second overtone. If we had a crazy standing wave with 5 nodes, it would be the 5th overtone. The number of antinodes tells you the harmonic name. If it has 3 antinodes, it would be the 3rd harmonic. I'm going to use, there's all sorts of permutations, but I'm going to use the mnemonic NOAH. Nodes and overtone name goes together. Antinodes and harmonic goes together. If you know the name tells you the number of nodes or antinodes. From that you can draw the standing wave, and from the standing wave you can figure out the length or the wavelength or whatever. I think I forgot to type it, but the length versus the number of football things. This one, their top one, had 1 football shape, and the length was 1 over 2 lambda. This second one had 2 football shapes, and its length was 2 over 2 lambda, or 1 lambda. This one has 3 football shapes, and it's 3 over 2. The next one had 4 football shapes, 4 over 2, which is just 2. If I do the next one with 5 football shapes, L would be 5 over 2 lambda. So there's a connection between number of footballs and the length as well. This was all kind of a lot, and it sets up how musical instruments work. So if you're a little bit rattled now, and we've done this before where at the end of a lesson you maybe isn't clicking perfectly, don't freak out. I'm going to stop this video, but you work through these 3 examples and the solutions there will help this click all together. And if it doesn't, just shoot me an email and we'll figure it out together. And finally, to remind you, there's another entirely different tutorial clip posted, one that I made a few years ago, a worksheet with answers for you to practice, and there's your check-in for this topic. Hopefully it clicks after doing the 3 examples, but as always, email me at any time.